Thank you all for coming out this afternoon. And to start off with, the title of this is Understanding the Equivalent Rectangular Stress Block. And I want to acknowledge my co-authors on this. You've already heard from Anahid earlier today, and then Ben is the co-moderator, so you've already heard from him as well. And so this is going to cover a couple of different things. So I'm going to start off and just give you a brief overview of equivalent rectangular stress block, which I would imagine most of us have heard over and over and over over the years. And then briefly just talk about the pedagogical approaches that were used by all of us, and then talk specifically about the three methods that we use when we do this, and then also just a couple of lessons learned. To start off with, this is generally what you see when it comes to equivalent rectangular stress block in a typical reinforced concrete class. Most of us, depending on when we took reinforced concrete, this may be all that you saw. It may not have been, maybe there were more examples, but in general, we had someone draw a two-dimensional strain and stress profile on the board that's actually at 90 degrees of the way that it's actually acting. And so I remember myself as an undergrad, it took a little while for it to click that, what was this actually represented. And I try to always tell my students that this actually represents strains and stresses coming out of the board at you. And then we wrap it around to the side because we don't have the technology quite yet to draw in air. But this is kind of what you see, and we know that there's relationships between the depth of the neutral axis and A, which is represented by Beta1. We talk to students about calculating the strain in the tensile steel. We talk about calculating the depth of the equivalent rectangular stress block, and then calculating the nominal moment capacity. And that third equation there, A is equal to ASFY divided by 0.85 F prime CB, is a lot of times all that students get. And there's not a lot of discussion about where that actually came from. And so this kind of gets into more of that to really understand what that means. And to understand that, there's a couple of things that go along with that as well. One of them is Beta1. And I usually show a chart similar to this in my classes to explain what Beta1 represents. And we always talk about, Beta1 is constant with F prime C less than 4,000. It's constant when it goes above 8,000, and then it changes in between 4,000 and 8,000. But we really don't always talk about why that is. And I was given a presentation at the professor's workshop a couple of years ago, actually, and Jim White came up to me afterwards, and we had a good conversation about Beta1 and how to visualize that. And these three figures actually came out of that. And it's a simple way to kind of help visualize what Beta1 does and what the 0.85 F prime C does as well. And so the point is to create what it says, an equivalent resultant force with roughly the same location for the resultant. And so looking at the figure on the left, you've got a 4,000 PSI concrete, and you've got a Beta1 of 0.85. And so you can see that the rectangle is kind of flat and wide. And then as the concrete strength increases, it becomes more narrow and becomes taller. But Beta1 is decreasing as you increase in that concrete strength. And it's a great visual to show students what that means. And in a lot of cases, that right there is simple enough to help students understand things, but we can go a lot deeper than that. And so to kind of hit the pedagogical approaches of this and where this came from, you can go back and read some things on learning styles. And I would go a little bit further to say learning preferences. So how do people prefer to learn? And there's a survey that's been around for years that's done by Felder and Silberman that's called the Learning and Teaching Styles or Index of Learning Styles questionnaire. And it'll tell you what kind of preferences you have. It doesn't mean you can't learn other ways, but it'll tell you the way that you prefer to learn. And one thing that we consistently see with engineering students is that they're active. They like to do things with what they're learning. And I would say about 3/4 of them are visual, meaning that they want to see something in action rather than you just telling them, here's an equation, go with it, right? So how do you apply that? And so to give you a little background on my part of this presentation, I was tasked with creating a visual for a topic in my discipline when I was taking an engineering education class at Virginia Tech to describe what I do to someone from a different discipline. And I had this idea of creating some styrofoam blocks, to represent how the stresses distribute in reinforced concrete. And the professor said, you should do this when you teach the class. And so I have been doing that since the fall of 2007, actually. And so to give you a little more background on the pedagogy side of this, if you were in the first session, you heard Matt Swinney talk about, active learning, and he went over a series of examples of that. But basically, a short summary of that is active learning is an instructional method that engages students in the learning process using meaningful, and I would go as far to underline that, more in-depth learning activities in which students take ownership of their learning experience. So if you're going to do something like this, it needs to be meaningful and have a purpose, not just something to keep your students busy. The primary objectives of active learning are to promote student activity and to engage them in that learning process. And so I've got some references here. If you ever want to dig into those, you can. And then the pedagogical approaches that specifically apply to this, you've heard about skeleton style notes twice already, and I think you probably heard about that a couple of times in the previous session. But it's note handouts, and I put in brackets here, or physical handouts, because it doesn't mean you have to write on paper. In my case, it's going to be styrofoam blocks, are created without key concepts or without key steps in the example problems. Students must listen to lectures and fill in missing information. And then physical artifacts, which we'll see with Anahid here in a second, provide a physical representation or model that can be visualized and explored in class. And so this one doesn't get into a lot of the complex active learning methods that you saw previously. I know Casey just talked about some of the more complex, like project-based experiential learning. These are more simple, right? This is something very simple you can do in class just to get your students engaged in that learning process. So starting off with method one, what I'm calling a visual learning activity. The objectives that I have for this when I do it in my class is to convert the depth of the neutral axis to the depth of the equivalent rectangular stress block, and to simply identify all of the terms in association with the nominal moment capacity of a rectangular beam. Now that seems very simple, but for a student that's seeing this for the first time, you have to remember that some of these things are not that simple, and being visual like this can really help students understand that. And so one side note here, I know we've talked a lot about class sizes and how to do these things and what works and what class size and everything. I've done this in a class as small as, I think I had 8 students at one time when I taught, and I've had a class as big as 65 students, and I've done the same activity, and it works just as well. So imagine that you've got a simply supported beam, and we cut a cross section of that beam. So I come in here and cut a cross section, and we look at it in 3D. So you're going to see the cross section on the bottom right corner of the screen here, and you would see the rebar in that, and the horizontal black line that you see there represents the neutral axis. So everything above that's in compression, everything below that we assume is cracked and no longer carries any tension. What I do in my class is I draw this out, and then I say, all right, so we're going to take a slice of this beam. And I give my students each a styrofoam block that's 8 inches by 4 inches by 2 inches. It has this exact same drawing on it. So you have some Sharpie drawn rebar, you have the neutral axis, and they each get their own. Now for the instructor block though, mine needs to be a little bit larger so that students can actually see what's going on. And so what I've done is I've created a foam core board version of this. And in the paper, if you get a chance to read it, I'll actually have this laid out there. It's the guide to how to make that block. And so I make this out of foam core board. I have all the dimensions on there. And so that I don't forget anything, I write everything lightly in pencil. So it looks like I remember everything, but I'm just actually cheating a little bit so that I don't forget stuff as I go. So what I do is I cut this out of foam core board. You can see the pencil marks here. These are a little bit too dark, it kind of gives it away, but and then you fold that up into a 6-sided box and create that for class. The reason is so it's larger so you can hold it up and students can see what's going on. This is the finished product of that block for the instructor block before things begin. right? So on the left, you can see the front and one side, and on the right, you can see the back and the other side. And you can notice there's a variety of things labeled on that block. And so when we go through this process, there's actually 18 steps to this in class, and I have them written out in the paper, but I've broken them down into 10 photos here on the screen. The one on the upper left is before you start anything. So you have the horizontal line, you have the rebar, and then the first step is I tell the students to write the word cracked and draw an arrow down below the horizontal line, indicating that we assume everything is cracked. And then we label the neutral axis, and then we draw the actual parabolic stress distributions on the sides. After we go from there, we switch to a red Sharpie and we label the depth of the equivalent rectangular stress block. And then we proceed to kind of color that in, label the top as 0.85 F prime C, and locate the resultant compressive force. And then we flip it around and go to blue, and we do our B value on the back, so the width of a rectangular cross section. And then we label the distance from the extreme compressive fiber to the centroid of the steel. And if you notice here, I did an unsymmetrical layout of reinforcing on purpose. And that's so that they have to think about where the centroid of the steel is. And I did multiple layers again because of the difference in D and D sub T. And so as we progress through that, we end up drawing the resultant tensile force. We draw the moment arm, which is D minus A over 2. And then finally, we finish it off with labeling D sub T on the back and talk about how we calculate strains. Students are allowed to use these on their exams. It's part of their crib sheet. And so this is what the final products look like. On the left is my finished instructor block. I have a stockpile of these from over the years. I think right now I've got about 6 stacked up in the lab. And on the right side is the student block. So mine is 12 by 8 by 4, and the student block is 8 by 4 by 2. The way to do this, the easiest way, is to get the styrofoam, the big blue board styrofoam, and simply cut it up into chunks. It'll cost you about $50 for a whole sheet, and it'll do you for a couple semesters, depending on the size of your class. Now, the second method kind of goes back to what you saw from Anahit earlier. And the objective of this is to assist students with visualization and aid in their understanding of the equivalent rectangular stress block. And so if you look at the progression of strains and stresses as a beam is loaded, case 1, for example, the compressive stress in the concrete is less than about half of F prime C. We assume that everything remains linear elastic at that point. And so you have a triangular distribution for the concrete stress. Case 2, it exceeds that, and so you start to get into that parabolic behavior. So the concrete starts to crush a little bit, and we represent that with a parabolic shape that's extended throughout the cross section. And in case 3, we have the idealized stress distribution that is drawn as a rectangle, and we incorporate the alpha 1 or the 0.85 F prime C along with the beta 1 value to convert from C and A. And so students tend to struggle with understanding, when do I use the triangular distribution? When do I use the rectangular distribution? When does the parabola come into play? And so what Anahit did is created these models, which you saw earlier, to help students visualize that and to explain, this is when this case applies, this is when this case applies, and this is when this one applies. And so it's just a different way of showing that. And so you've got the idea that students are creating something in class, and then you have also the idea that you are showing them a more detailed version of this. I love this because it shows the detail. It shows the rebar coming, the stress from the rebar coming out, and the stress in the concrete. And then lastly, looking at something similar, you can break this down as simple as using a 2x4. And so we want to guide the students in creating their own physical model to visualize the equivalent rectangular stress block. And so Ben created this option with simply using 2x4s. And so it's the same concept, it's just visualizing it with a different type of material. And so really it's kind of a personal preference in the way that you want to do that. So you can see the different views here of the 2x4. You've still got the resultant compressive force, the resultant tensile force, your moment arms, and everything's still labeled. And so just a couple of lessons learned here to finish up. Method 1, it takes about 2 hours to create the larger instructor block. an additional time to cut the styrofoam blocks and add the rebar and neutral axis location. I recommend grad students help with that. Method two, it takes time on the front end to create the models. But you know, I think anytime you create something like that on the front end, there's going to be a little prep time once they're created. And then lastly, with the 2x4s, again, it's going to take a little time on the front end. And I know Ben mentioned to make sure you sand the edges to prevent splintering when you're doing it. Overall, students have noted to all of us that both formally and informally, that the various models help them to visualize the concept better than just simply looking at 2D versions. And so with that, if you have any questions, I'd be happy to answer that. And Casey's holding hers up from when she sat in one of my classes before.